Okay, so I want to thank the organizers for the wonderful conference and for all of you who stayed to the bitter end. So I'll talk today about imaging quantum oscillations in various van der Waals materials. This is our experimental technique. We have a tiny squid on a sharp needle attached to a tuning fork, which allows us to scan the sample a few tens of nanometers above the surface, and it allows us to image local magnetic fields and also local temperature distributions, but today I will not talk about thermal imaging. So, and actually we can image any sample in practice. Okay, now it will work. So the heroes of the things that I will present today on the experimental side are Nadav, Mati, Haibiao. Nadav is here, Haibiao, Indranil, and Matan mainly. And on the theory side, it's Patrick, Dan, and Gal, who is here, as well as Leonid, Binghai, and Yuval Oreg. This is not good. Hope it works. No, it doesn't. Okay, so I'll switch it like this. So quantum oscillations, and that's a pity it doesn't work.
You can press it really hard, it breaks.
Press this hard? No. Okay. Anyway, so quantum oscillations arise from Landau levels, and you can see it in various observables. And so the most famous one is, no, this is a different one. Yeah. Let me restart it. Okay. Doesn't work. Okay. Anyway, so quantum oscillations should appear in any observables, and we've seen a lot of almost any experimental talk shows you quantum oscillations in resistance, which is Shubnikov de Haas. But of course, there should be also quantum oscillations in magnetism, which is the de Haas van Alphen. And de Haas van Alphen has not been observed so far in van der Waals materials, and in fact, it has several advantages. The most important one is that it's thermodynamic property of the band structure, so you don't need to know anything besides the band structure. It doesn't involve any scattering, and therefore it allows very accurate quantitative analysis and band structure reconstruction, including interaction effects. And as we'll show today, you can also perform that at very low magnetic fields, and you can do spatial result measurements, namely you can reconstruct the local band structure. And the problem, of course, is that the magnetic moment is proportional to the volume of the sample. So traditionally, de Haas van Alphen has been used in metals and semiconductors to study band structures, but if you go from a millimeter three-dimensional sample to micron size, two-dimensional sample, you lose like 12 orders of magnitude. So obviously, the traditional methods for imaging the Haas van Alphen are inapplicable to 2D systems. So the way we do it is, again, with our squid on tip. So I'll show you today 3 examples. One is, the first one is just Bernal ABA graphene. So this is the band structure, and if you apply small magnetic fields, you will have Landau levels, and this is the oscillations that we will be looking for. So our experimental setup is like this. We short the sample, so we have no currents in the sample. We ground the sample, we apply a backgate, which defines the overall carrier concentration, and we apply a small AC voltage to modulate the carrier concentration. And what we measure is the corresponding change in the local magnetic field due to this small modulation. Namely, we take this derivative, and what is important is essentially magnetic fields are transparent to insulators and to metals, so we can actually study samples encapsulated in top metallic gates, which allows us to apply displacement field, which is an important parameter to change the in situ band structure. So I'll show you now this signal, the local signal that we measure, as a function of carrier density over a relatively small range between -1 and 10 to the 12. And this is how it looks. So we observe over 100 quantum oscillations. And as I said, this must be a thermodynamic property, so all we need to do is to take tight binding model, assume some parameters, calculate the quantum oscillations, fit these parameters, play with these parameters until we get a good fit, and this is what we get. So there are two remarkable things to me here. First is that actually one can measure so beautifully quantum oscillations, in this case, hundreds of them. And the second is that actually such a simple tight binding model can reproduce the band structure to such a high accuracy, including all the fine features that you can see in the experiment. So from this, we can extract very accurate band structure parameters. So these are all the hopping parameters. This is the Dingle broadening that was previously asked, so it's like 0.3 millivolts. And once we know the band structure and we do the calculation, we can map out, we can know exactly what are the different Landau levels. So the dense lines here are the dense Landau levels in the bilayer sector, and the sparse Landau levels are in the Dirac sector. So this was at zero displacement, but now we can apply also displacement field, which should hybridize the Dirac and the parabolic band, opening a gap in both sectors. So this is how the experiment looks. So this is the displacement field. This is the carrier density. So what I've shown you previously was the long zero displacement field. So now we already know the band structure, and we can easily add displacement field. And this is what we get theoretically. So really, all the fine features are reproduced very nicely, essentially with zero fitting parameters here. And again, from here, we can learn a lot about the different Landau levels and the different splittings. So for example, this is the first Landau level in the Dirac band. And these are two zeroth Landau levels which sit at the extrema points of the Dirac band, so the splitting. So for example, when you cross, so the dense ones are the blue, and the sparse ones come from the Dirac band. And when you cross, one of the Landau levels in the Dirac band crosses the parabolic bands, you have a 2 pi shift because all the Landau levels are 4-4 degenerate. But when you cross the zeroth Landau level, you have only pi shift, and this is because the zeroth Landau level is 2-fold degenerate, where all the rest are 4-fold degenerate. Another interesting observation is that you see these high Landau levels have this dark signal, which is diamagnetic response, whereas the zeroth Landau level has no signal. It looks just like a ghost that just changes the phase of the other Landau levels, but has no signal by itself. And the reason is that the zeroth Landau level has zero momentum, and therefore there is essentially no orbitals, and there is no diamagnetism associated with zeroth Landau level. So what I've shown you so far was at relatively low densities up to 2 times to the 12, but we can go to almost an order of magnitude higher densities. And this is now two-dimensional imaging of the orbital magnetization. So at low densities, the Landau levels are quite flat and uniform. You see quite uniform magnetization. But as you go to higher fillings, you start having inhomogeneities. And this is the line cut. So again, this is position here, and this is the carrier density. So if we look at 2 points, for example, point A somewhere along here, we see these quantum oscillations, as I've shown you previously, but now over a much wider range. And we know already the band structure, we get a very nice fit. But now let's look at this point somewhere here, and what you see is that there is some beating. There is envelope. So you see, for example, here quantum oscillations appear, then disappear, appear, disappear. So obviously there is some interference or some beating between two very close by frequencies. So this is at magnetic field of 300 millitesla. We can go to even lower field. This is 170 millitesla, and you see that this beating becomes denser, goes to lower indices. So there are various possible. So obviously there has to be two slightly shifted Fermi surfaces or slightly shifted Landau levels. And there are various possibilities, and we can show that actually that it comes from shear-induced strain, which causes pseudomagnetic field. So Paco and others have shown us that if you take a strip of graphene and tilt it or bend it by angle theta over distance L, it creates a pseudomagnetic field proportional to theta over L. And if you put in numbers, a twist of 1 degree over a distance of about micron gives you a pseudomagnetic field of 1 Tesla. And of course, STM studies and others, Eva is here, have studied pseudomagnetic fields arising from corrugation, which gives pseudomagnetic fields of 100 Tesla and more. So as I said, we know already the band structure, and now we will have, so the pseudomagnetic field doesn't break time reversal symmetry, which means that it adds positively to K valley and negatively to K prime valley, which means that the Landau levels in the K prime valley will have slightly lower period, which means that at some point they will be out of phase and cause some destructive interference between the two valleys. So we need only one parameter, which is pseudomagnetic field, and we can look for best fit, and this is what we get. So this is the fit, which gives us a pseudomagnetic field of 4.2 millitesla. We can do a sanity check and then go to a lower magnetic field, and now it's a fit with 0 parameters because we already know the pseudomagnetic field. So we can repeat this as a function of position, and this is what we see. So we see pseudomagnetic fields in the range of 1 to 6 millitesla. So this is 5 orders of magnitude smaller than the pseudomagnetic fields that have been previously observed on the order of 100 Tesla in...
I'm slightly confused. If your Bingo temperature is 4 Kelvin, how...
No. 4 Kelvin.
How do you see a 4 millikelvin pseudomagnetic field? I'm totally confused.
So you see, because we can see like 500 Landau levels. So very small displacement.
No, say no more. I got it. Thank you. This is an incredible experiment.
Thank you. Otherwise, you wouldn't be able to say. So each Landau level, you cannot distinguish them, but you accumulate 200 of them.
Such fantastic oscillations into this.
Absolutely. This is what is drawn here. So, oops. So you see, if you have many of them, eventually you will. Okay, so, but what amazes me is that essentially we have regions of few microns that have a pseudomagnetic field of less than millidegree, which is our minimum resolution determined by how many Landau levels we can actually map out. And which means a 1 millitesla pseudomagnetic field translates to a twist angle of 1 millidegree. So essentially you have regions in the sample in which the atomic lattice is aligned to within 1 millidegree. And this is only because it's a crystalline graphene, in my opinion, ABA, in this Bernal trilayer. And it also, the strain is just given by the angle, so it's less than 10 to the minus 5. So we can actually map out shear strain on this sensitivity. And this one has to bear in mind that in typical magic angle graphene, the twist angle is 0.1 degree, which means that it will give us local pseudomagnetic fields of the order of 0.1 Tesla, which is another sort of disorder parameter that we usually don't take into account. We think of band structure, but we usually don't think of pseudomagnetic fields on a large length scale. Okay, so now we switch to another example, which is bilayer graphene aligned to HBN, as we have heard several talks about this. And so again, very similar setup. This is two-dimensional imaging of the quantum oscillations. So this is X, Y, and this is a very small range of filling parameters. And you see they are quite inhomogeneous. And we can now take a line scan instead of 2D. And again, this is the position, and this is the filling factor now over a large range. And here we see about 500 Landau levels. They're too dense to see them on this plot. So we can zoom at specific regions. So if we look here, we see very nice periodic quantum oscillations that correspond to fourfold degenerate Landau levels. If we look here, we see much lower frequency oscillations, which vary with doping. And for example, in this region, we see multiple low frequencies coexisting. So as I said, there are too many of them in order to count or to account for them individually. So what we do, we take a small window of about one nu of 1 and do FFT on this window and move this window. And this is the FFT that we obtain. So in this region, okay, I'll skip this. I'll explain it in more detail here. So this is the folding. So this is the band structure of bilayer graphene in the minimum zone due to the Moiré periodicity. And you see that actually the bands are separated by very small gaps, and most of them actually overlap in K-space. And if we take a cut, let's say, at this energies somewhere here, so we see 3 pockets, an electron pocket and 2 hole pockets. And in this case, we should have 3 frequencies. And usually, the Shubnikov-de Haas oscillations are taken or analyzed as a function of 1 over B. But we actually change the carrier density. So in 1 over B, the ratio of the frequencies should be given by the ratio of the Fermi surfaces. But as a function of n, the ratio should be given by the density of states. In fact, but the same sum rule applies, so it doesn't matter so much. So we can easily, given some band structure, we can easily calculate the density of states of each of the pockets and just derive these expected frequencies and fit them to the experimental results by changing the band structure. So this is the fit. So for example, here now we have a single Fermi pocket here, so this is this line, which corresponds to a frequency of 1 in the units of phi naught over 4 magnetic field. And these are the different Fermi pockets, each giving different frequencies, and we can get a very nice fit. Namely, we can reconstruct the band structure quite accurately from these quantum oscillations. And the main finding actually is that the lattice relaxation is significantly larger than what is usually assumed in the literature. So these parameters are usually taken to be of the order of 1. And this larger relaxation actually gives rise to more overlapping bands, mini bands, and to smaller band gaps. So now if we look closely, so for example here, so now we're looking on the electron doping. We can explain very nicely some of the frequencies, but for example, this frequency does not come up from the band structure. So for example, if we look here, this is the band structure, but now if we look at the expanded beryllium zone, So here we have 3 pockets, 2 red ones, which give these 2 frequencies hole-like and, electron-like, and this is hole-like, the purple one. But what is this frequency? So we can start guessing. And for example, we can imagine such a trajectory. So this trajectory will enclose 2/3 of this pocket, 2/3 of this pocket, and 1/3, this part plus this part, of this pocket. Since we know the frequencies of each of these pockets, we just have to take the linear combination, and this is what we get. So this frequency is this linear combination, and now you have to ask yourself, how come the electron tunnels between different pockets? And this is due to the magnetic field. So in presence of magnetic field, you can tunnel, right? Just Lorentz force, you can think of it. This is called magnetic breakdown. And it is characterized, the tunneling probability is given by this magnetic breakdown field, which is proportional to square of the gap in the K-space. So we see magnetic breakdown at below 300 millitesla, which means that the gap has to be less than 0.01 nanometer. And if we do a line cut here and look at the dispersion, so these are the 2 pockets. And you can see over a wide range of energies, they're very close to each other. So if we zoom in, the gap between them is 0.005 nanometers, less than what is required, which explains the existence of this trajectory, which is essentially a coherent electron-hole state. So it has to be coherent in order to have quantum oscillations, and you hop between electron and hole pockets. If we look at the hole doping, we see again the various other mysteries. And again, this band structure is like this. And if we take a trajectory like this, for example, we get exactly this missing one. But what is important here, that the gaps here are even smaller and there are sharp corners, which enhances the hopping. So hopping, the magnetic breakdown is even stronger. So you can never, electron can never accomplish this purple trajectory because it tunnels, and therefore this line, which should have come from the band structure, doesn't exist. So this explains a puzzle that if you look at transport at high fields, very strange at low fields, you have Landau levels that go to the gap. So here you actually have a real gap. But if you go to high magnetic fields, very surprisingly, Landau levels extrapolate to charge neutrality, which doesn't make sense at the first glance. So if you look at the extended Brillouin zone and expand it even further, and now we're at several Tesla, so the magnetic field is much larger than the magnetic breakdown field, which means that your hopping probability is essentially 1. So imagine an electron being here. Once it comes to the junction, it must hop. It cannot accomplish this trajectory. So and if you follow this trajectory, this is exactly the band structure of your original bilayer graphene. So essentially, your magnetic field fully unfolds the Moiré potential, and at high fields, the electrons are not aware, essentially, that there is a Moiré potential because of this magnetic breakdown. Okay. So now I come to the last example, which is probably most interesting, and this is a strongly intrinsic system, which in this particular case is twisted tri-layer graphene, alternating twist angle graphene. So this is the band structure. So the flat bands are as in the magic angle bilayer graphene, but it has an additional band, which is Dirac band, and they coexist. But the beauty is now that this additional Dirac band, because it has low density of states, the Landau levels are well defined there. And this allows us, it actually forms a built-in spectrometer. So we know exactly, at a given field, we know exactly the energy of the Landau levels in here. And we know the density. The density, this is just the density of each Landau level. So now if we dope the system and if the bands are rigid, we will just know exactly where our Fermi energy is and how many carriers go into the Dirac and flat bands. So we do this experiment. So these are the quantum oscillations in this tri-layer graphene. And this is position, again, along the sample, and this is the carrier density now on the whole side. And the first thing that we see is by the time we reach four-fold filling, namely once we fill the flat bands, we can count 9 Landau levels in the Dirac band. But this doesn't make any sense because by the time we fill the Landau levels, the flat band, we should have filled only 1, at most 2 Landau levels in the flat band, in the Dirac band. But we actually fill 9 of them. So obviously single particle picture doesn't work, so we have to add interactions. And the first thing we can do is just to add the Hartree potential. So we know that most of the wave functions in the flat band reside on the AA, which gives charging self energy and a periodic Hartree potential within the unit cell. So we can easily calculate that. And again, instead of having rigid bands that we fill, now the bands will be distorted by this Hartree potential. And in particular, at K points, where most of the charging energy comes in, the bands are significantly distorted, whereas at gamma point, they're hardly changed. And by the time we reach, by the time we fill the flat bands, our Fermi energy is now at about 50 milli-electron volts, which is exactly 9 Landau levels, which we see here. And once we continue filling the dispersive bands, the density of states here is much lower, which means that the Fermi energy moves faster, and this results in this higher frequency oscillations that we see here. So far we've used the ruler of energy, but actually we have also another ruler of carrier density. We know exactly how many carriers go into each band. So we know when we go from one Landau level to another, we add total dn to the system, but only a very small fraction, the degeneracy of the Landau level, goes into the Dirac band. So now we can calculate this from our data, and we see that by the time we fill the flat bands, about 10% of the carriers go into the Dirac band. But in the single particle calculation, only less than 1% should have gone, should have gone to the flat band. So now we can take our Hartree calculation and compare, and this is what we get from theory, which reproduces the data very nicely. So we see that by filling the bands of the flat band, about 10% of the carriers go into the Dirac band because now the Fermi energy is much higher. So essentially the bandwidth is highly renormalized by the Hartree potential, which is the main takeaway message here. And we can reproduce all the rest of the features.
And what about the Higgs temperature here?
Again, you see, we cannot see the Landau levels in the flat bands. We see the Landau levels only at these low fields, right? We're talking here about, I don't remember, yes, 250 millitesla. So that's why we can see only the Landau levels, and those are spread by several millivolts.
Several millivolts.
Oh, yes. Yes, right. So there, it's very easy to see the Landau's there. So that's a trick, essentially. Because we're interested in high density of states systems, and high density of states, you have very dense Landau levels. Essentially, you cannot see them at low. You have to go to very high fields, which changes the band structure by itself and so on. Okay, so this was on the whole doping side. If we go to electron doping, we see Stoner instability at nu equals 2, but I will skip this. We can discuss it later. So the main point that I wanted to present, and this is last slide essentially, is what happens at charge neutrality. Okay, so now we have additional knob that we haven't used so far, and this is the displacement field. So let's think of a single particle picture. The Dirac band and the flat band, they coexist, or they overlap at charge neutrality, and if we turn on now the displacement field, they will hybridize and open a gap, and the Dirac point will shift up in energy here, and the same thing, just enhanced, will happen in the Hartree case. The Dirac point will move up, but just more significantly. So what we expect, and the zeroth Landau level should be at the Dirac point, which means that the zeroth Landau level should move up and all the other lambda levels should move up with it as a function of displacement field. And the same thing for hole doping. Now we're talking about this point, all the lambda levels should move down. This is the expectation. But now we do this experiment. So again, these are quantum oscillations as a function of doping and displacement field, and we see just the opposite. So the high lambda levels above filling of about 2 or so, they indeed bend away from charge neutrality as expected. But the lower lambda levels, you can see they bend towards the charge neutrality, just the opposite of what we expect. And most importantly, the 0th lambda level stays put at charge neutrality. This means that this picture cannot be applicable, right? So, so for this, and we can go even to lower fields. So this is now 56 millitesla. So we can see quantum oscillations at 50 millitesla. And again, we see that lambda levels below about 1.5 all bend towards the charge neutrality, and the 0th lambda level remains at charge neutrality. So we have to add Hartree or at least to try to. And there are, as you know, there are a lot of possible ground states that have been described theoretically at charge neutrality. We can divide them into two possibilities. One is ungapped state, and we know only of one case, which is nematic semimetal, as was mentioned by Sid and others, or a gap state, which the main one that is studied very intensively is the KIBC. So let's look at the nematic semimetal. So in the nematic semimetal, the nodal points of the flat bands move away from the K point towards gamma, spontaneously breaking C3 symmetry. And now if we apply displacement field, the hybridization, rather than occurring at charge neutrality, it now occurs at the Hartree-Fock energy of about 25 millivolts. So nothing happens at charge neutrality, which means that the 0th lambda level should remain at charge neutrality exactly as we see. But also now the Fermi velocity is renormalized. It is lowered below the hybridization energy. So we expect the lambda levels here to bend downwards, while the lambda levels above actually are pushed upwards. So this is exactly what we observe. Now let's look at the other possibility of KIBC state, for example. So again, there is no overlap at the Dirac point. So in this region, very similar effects should happen. The 0th lambda level should remain at charge neutrality, and the velocity should be renormalized. But the difference now is that there are no states in the flat bands. So if we look more carefully at this low magnetic field data and plot the oscillations, so we can do the same trick, calculate how many carriers go into the Dirac band and into flat band. So we find that about 3% of the carriers go into the Dirac band. So now let's look at our first lambda level here. At this magnetic field, it occurs at 7 millivolts. 7 millivolts is here. So there are no states in the flat bands, which means that 100% of the carriers should have gone to the Dirac band. But we see that only 3% goes to the Dirac band, and 97% go into flat bands, which means that ground state cannot be gapped. Okay, I repeat, if the ground state is gapped, all the carriers up to hybridization energy should go into the Dirac band. But we see that a tiny amount goes into the Dirac band, which means that the picture should be like this. So now if we take these Hartree-Fock calculations, we can calculate, as I said, how many carriers go, and we indeed find that about 3% go into the Dirac band. So there are two main observations. It's first that the hybridization does not occur at the K point, which means that the nodal points of the flat band are not at the K. And second, that the ground state is not gapped, and the only possibility that is known in literature that is consistent with this is this nematic semimetal. And since very few studies have looked at it carefully, this is how the band structure looks. These are the K points in the Dirac band, and these are the nodal points in the flat bands. So I encourage the theoreticians among you to take a closer look at this possible state. So let me just summarize. So first of all, we have shown that the Weizmann alpha and thermodynamic quantum oscillations can be imaged with very high precision and locally and at very low fields. We find pseudomagnetic fields, and we have sensitivity to find magnetic fields on the order of millitesla. In this twisted trilayer graphene, we see a strong effect of the Hartree potential. We also see symmetry breaking that I didn't have time to describe, and the nematic state that we believe occurs at charge neutrality. And let me leave you with this movie, which is the Bernal bilayer graphene on HBN, how the quantum oscillations change with position. Thank you very much.
Thank you. I'm just going to make sure I see who is raising his hand. Put the lights back on.
Thank you.
Any questions? Okay, yeah, and then we go to take questions.
Absolutely fascinating stuff. Let me ask you a question on the Bernal bilayer graphene. So the fact that the tight binding, single particle tight binding model gives such good fitting, is that what is leading to a conclusion is non-interactive? I mean, a priori do not know whether a system is interacting or non-interacting. Sure. But the fact that tight binding fit is so good there and not in the twisted trilayer is what leading. So that's like one very important message. That
I agree. This is the message that I want to convey. It doesn't mean that the hopping parameters don't take interactions into account.
Yeah, no.
But the tight binding model works
maybe
perfectly.
They become quasi-particles, but they do not, there is no massive failure. But the second question, I'm absolutely fascinated by your Dingle temperature of, something like
0.3
yeah, 0.3. So that's 4 Kelvin. So why is it the party line is that, graphene is very pure? I mean, gallium arsenide, 4 Kelvin, it's 4 samples away. I mean, if it's, so graphene is not very pure. 4 Kelvin is a huge Dingle temperature.
Okay, big or small, it's our interpretation. But I want to make a point that people have estimated Dingle temperature from the Weizmann alpha and even from capacitance measurements and so on. So usually you get in ABA graphene, you get numbers of 1 to 2 millielectron volts. We see much smaller ones, and this is because we measure locally. Mm-hmm. Transport or capacitance, it averages over this. So much of the broadening is not Dingle broadening, it's large scale.
So your single particle broadening is smaller than the transport broadening.
Exactly.
That's what I'm leading to. Okay,
exactly.
So because you are directly measuring a single particle self-energy.
Right.
And that is
in
like
a small area.
Factor of 3 smaller. So there is some, the small angle scattering is, there is a lot of small angle scattering here also.
True. But again, if you put in numbers at these low magnetic fields, your trajectories, sort of naive trajectories, are larger or comparable to your sample size.
Aha.
Okay, so maybe scattering at the boundaries is actually the one that determines this.
I was going to ask, are the impurities far apart? You just told me they don't have to be far apart.
Exactly.
They could be just at the boundary. Thank you very much.
So, on the last bit, you talked about the nematic semi-metal and you showed some comparisons. Is it, do you have the resolution to see whether it's the actual thing that breaks C3 spontaneously or the strain-induced version of this, where, it's not spontaneous breaking, but there will be some details of the band structure that are maybe not quite so sharp?
Obviously, you see, this is the quantum oscillation is a function of position. And obviously, there is a disorder, strain, pseudomagnetic fields, whatever. Whether this is the cause for the nematic semi-metal to be the ground state, or it should be there in the first place, this you guys should tell us.
Any other questions?
So let's say you go to the lowest fields that you can measure at. You look at any piece of graphene or graphite. Do you ever not see a quantum oscillation?
Again, it depends on the density of states. So if you take just...
I just mean as like an empirical question. Like, have you ever seen a piece of graphite that didn't have magnetic signal?
No.
Oh, yeah, I'll see that.
By the way, I didn't. Okay, it's not on this slide, but if you look at the amplitude of the signal and extract what is your magnetic moment, you reach hundreds of Bohr magnetons, even sometimes 1,000 Bohr magnetons per electron. It's something that we don't think of, but quantum oscillations have huge, at low fields, have huge orbital moment. But let me just, to follow up on your question, right. Doesn't work. Okay, so here are quantum oscillations at 14 millitesla. Okay, so again, this is the tri-layer, the ABA graphene, and this is what. So once we decrease the magnetic field, we first lose this. So on energy scale, these Landau levels at 300 millitesla, here they're about 0.6 millivolts separated. Here they're about 1 millivolt separated. So you can clearly understand that 0.3 is enough to see them. But as you lower the magnetic field, you start losing first the dense ones, but these, the monolayer one, survive up to, as I said, 40 millitesla. And maybe just one more point is, yes, regarding Dingle broadening. So you see, so this is just calculations. So this is Dingle broadening from 0.2 to 0.8. So you see here the magnetism, Bohr magneton per electron is about 1,000, okay? And the Dingle broadening drops it very fast. There's dense ones, so here you reach about 10. So when you change from 0.2 to 0.8, you lose 2 orders of magnitude in these dense ones. But the sparse ones, you see they're about 100 here and they're about a couple of hundred here. So this is calculation, okay?
Can you use your technique to measure the gaps of the insulators at the other integer fillings away from neutrality?
Say it again.
Could you use your Dirac-Cohen spectrometer to measure the gaps of the integers of the insulating states away from neutrality?
Yes, in terms. So you see, in order for this trick to work, you need some reservoir. Mm-hmm. So the flat bands act as a reservoir, and the Dirac band is your spectrometer. If you have a gap, then the quantum oscillations will be extremely fast in the gap, and then again slow in this. So the answer is yes. So
you've done that, or?
So that's what we see in the slide that I skipped. Again, so what I've shown you in twisted tri-layer graphene was on the hole doping, but at electron doping we see these correlated states at nu equals 2. So if we look at the quantum oscillation there, you see that the frequency goes up sharply here, as well as this is also the ratio of the carriers that go into flat band. And you can explain it easily by just putting by hand Stoner. So at filling factor 2, if there is no Stoner, this would be your Hartree distorted bands. But if you add Stoner and you cause splitting, then in order to be at filling factor 2, you have to raise your Fermi energy significantly up. And now if you do the calculation, this is how the charge distribution should go. So this high frequency oscillations means that more carriers go into the Dirac band, and you can quantify it quite well.
And how big is the gap at 2?
Say it again.
How big is the gap that you get?
So we get like plus minus 25 millivolts.
So do you do these measurements on the same sample, or you have many samples?
So this twisted tri-layer graphene, we measured 3 samples. So this, what I showed you is one of them. We have data on
because
2 more.
my question is on this charge neutral. So basically this state that you seem to find, You see that in all three samples?
Yes, yes.
Okay,
You see,
so-
if the flat bands would be gapped, first of all, with the function of displacement field, they would bend the other way, and second, the low Landau levels would be extremely dense. You would fill them immediately,
Right. Yeah.
but you see that you have to put a lot of carriers into your system before you start filling the Dirac bands Landau levels.
Mostly because I was going into this comment from Sid, whether you have strain, and then of course the role of the strain.
So the
in
samples
this.
are very inhomogeneous, but everywhere we see that there is a large density of states at charge neutrality.
Thank you.
Okay, it's time, and I guess people have to get going on their way to the shuttles. But let's thank not only Eli, but all the speakers of today and of the entire conference, and also especially the organizers for putting together this very nice conference. So yeah, thank you.